Welcome to The Explainer. Today, we're digging into a really fascinating paper that gets right to the heart of the whole AI conversation. It's called The Illusion of Thinking, and boy, does it ask a question that feels more important every single day.
You see it everywhere, right? Headlines telling us that AI is starting to reason, to plan, to solve these incredibly complex problems. But are we really seeing the birth of true artificial thought, or are we just being fooled by a very, very clever magic trick? Well, some researchers at Apple decided to investigate, and what they found is absolutely essential for understanding where this technology is really at. So, let's start by looking at the models at the center of this whole debate.
The paper zooms in on this new kind of AI they call large reasoning models, or LRMs. Now, you've probably heard of some of them, like OpenAI's o1 or Anthropic's Claude 3.7 Sonnet with its thinking feature. The big deal with these models is that they're not just trained to spit out an answer. No, they're specifically trained, often with techniques like reinforcement learning, to actually generate a long, detailed thinking process before they give you the final result. The idea is to reward better, clearer reasoning.
And that's what makes them seem so incredibly smart. They literally show their work generating this long-winded chain of thought. It looks, for all the world, like the model is thinking through the problem, trying a few things, correcting itself when it messes up, and reflecting on its own steps, just like a person would. This is what creates that really powerful impression, the illusion of thinking. But here's the billion-dollar question the researchers posed. Is any of that process real, generalizable reasoning?
And that question leads us straight to the core problem the paper identifies. See, if we want to know if these LLMs can actually reason, we have to test them. But what if the tests we've been using are just, broken?
The paper puts it perfectly right here. Are these models truly capable of generalizable reasoning, meaning they can solve problems they've never seen before, or are they just using super advanced pattern matching? In other words, did they learn how to think, or did they just memorize the answers to the test from their training data? The researchers argue our current tests make it almost impossible to tell the difference.
The whole issue really comes down to what makes a good test versus a bad one. A lot of the benchmarks we use today are stuffed with common math and coding problems that are all over the internet. This creates a huge risk of what's called data contamination. The model might have already seen the problem and the solution during its training. That's not a test, it's a memory quiz. So to fix this, you need a good test. One that uses problems the AI has never seen before and lets you check every single step of its work, not just the final answer.
And look, this isn't just some abstract theory. The paper points to some really weird results from real-world math competitions. For example, some of the top AI models do worse on easier, more recent exams than they do on harder exams from a few years ago. Now, that makes no sense, right? It's a massive red flag. It suggests performance has less to do with actual reasoning skill and more to do with whether the test questions have had enough time to leak into the model's training data.
So, to get around these busted benchmarks, the researchers decided to build their own playground. They call it the Puzzle Gauntlet. It's a set of challenges designed from the ground up to be totally free of data contamination, creating a truly fair and controlled test of pure reasoning.
This gauntlet is made up of 4 classic puzzles that require real algorithmic thinking. You've got the Tower of Hanoi, a test of recursive planning, checkers jumping for spatial reasoning, the super tricky river crossing problem, and blocks world for planning and state tracking. The genius here is that these puzzles are defined by a few simple rules, not a bunch of facts from the internet. This lets the researchers dial up the difficulty with surgical precision, like just by adding one more disk to the Tower of Hanoi to find the exact point where a model's reasoning just breaks.
And here's the most brilliant part of their whole setup. When a model tries to solve one of these puzzles, it spits out its entire thought process and its final answer. The researchers then take that entire output and feed it into a custom-built simulator. Think of this simulator as a super strict referee. It doesn't just check if the final answer is right. Nope. It checks every single move the model made in its thought process to see if it follows the rules. This gives them an unprecedented move-by-move look at exactly how and when the model's logic falls apart.
Okay, so they built this incredible, contamination-free gauntlet and threw the world's most advanced reasoning models at it. And the results? Well, let's just say they were surprising. This is where that illusion of thinking really starts to show its cracks.
The first thing they found was this really clear pattern. On the easy puzzles, the standard non-thinking models were actually a bit better. Then, in that medium complexity zone, the thinking LLMs, the ones that show their work, pulled ahead. But then, as the problems got really, really hard, something dramatic happened. As you can see on this chart, performance for all the models just completely fell off a cliff.
And when I say fell off a cliff, I mean a complete and total collapse. Once the puzzles got past a certain difficulty level, a level that was different for each model, the accuracy for every single one of these advanced reasoning models dropped to 0. Not 10%, not 5, 0. They couldn't solve a single puzzle once it got hard enough.
But here is the strangest, most paradoxical finding of all. You would think that as a problem gets harder, a thinking model would, think harder. The researchers found the exact opposite. As the puzzles got close to that breaking point, the models started to reduce their effort. They generated shorter and shorter thought processes, basically giving up, even though they had plenty of processing power left to use. It suggests a really deep, fundamental flaw in how these models try to tackle hard problems.
The analysis of their so-called thoughts also revealed they're incredibly inefficient. For easy puzzles, the models would often find the right answer early on, but then they'd just keep going, overthinking the problem and wandering down all these dead-end paths. It's a huge waste of energy. For the medium puzzles, the right answer only showed up way at the end, after a whole lot of trial and error. So yeah, they can self-correct, but it is not a clean or efficient process at all.
Now, this next test might be the most damning piece of evidence in the whole paper. The researchers thought, okay, maybe the models are just bad at finding a solution, but maybe they're good at following one. So they gave them the exact step-by-step algorithm for the Tower of Hanoi. The task was dead simple, just execute these instructions. And the result? They still failed at the very same point. This is huge. It suggests the core problem isn't just about high-level planning. It's a fundamental inability to even follow a simple logical sequence.
When you put all this evidence together, it points to one conclusion. What looks like skill is probably just familiarity. For instance, a model could solve a 31-move Tower of Hanoi puzzle, which, it turns out, is a classic textbook example you can find all over the internet. And yet that same model would completely fail at a much shorter 11-move river crossing puzzle, which is way less common online. This strongly suggests the models are just pattern matching things they've seen before, not applying genuine reasoning.
So, what does this all mean? When you piece it all together, the total performance collapse, the bizarre thinking less paradox, the failure to even follow simple instructions, and this heavy reliance on familiarity, the picture gets a lot clearer. The thinking we're seeing might just be more of an illusion than any of us thought.
The paper's conclusion is blunt and it's powerful. They state that despite all their fancy bells and whistles, today's large reasoning models are failing to develop truly general problem-solving skills. There seems to be an inherent limit in their design that prevents them from scaling up to harder reasoning tasks. Simply making the models bigger or throwing more compute at them at inference time isn't going to fix this core problem. So let's just quickly recap the key takeaways. First, that thinking process we see from LLMs, it's not the same as flexible human-like reasoning. Second, their performance is incredibly brittle. It looks great on problems they've kind of seen before, but it completely shatters when faced with truly new, complex challenges. Third, their whole reasoning process is messy and inefficient. And finally, they can't even reliably follow a set of instructions, which points to their success being more about pattern matching than real thinking.
And that leaves us with this huge, lingering question. Now, this research isn't saying these models aren't useful. They are obviously incredibly powerful tools, but it forces us to be a lot more honest and precise about what they are. If their skill isn't true reasoning, but is instead an almost unimaginably vast and sophisticated ability to find and stitch together memorized patterns, what does that mean for the future of AI? What are we really building? And what's it going to take to get past this illusion and build something that can truly think? That's the challenge this paper leaves on the table for all of us. Thanks for joining The Explainer.